Right, we are focusing on the power method for actually our start today, and we're going to be looking at many more things that remain extremely important. But in this example, we consider the eigenvalue problem. Ax equals lambda x with the matrix A, which has the entries that have been shown there, and the inverse with the entries shown there. Okay, and then obviously the question is use the power method to estimate the dominant eigenvalue and the associated eigenvector, the eigenvalue of the least absolute value and the associated eigenvector. So this is very important for exam purposes, and we discuss this because there are just two components. Either two eigenvalues are the same or they're different. So if they have different magnitudes, then we are interested in then saying how do we use the power method to estimate the dominant eigenvalue and also to estimate the smallest in terms of magnitude absolute value. So let us solve this problem and show what needs to be done. But we'll mention the following here. Right, in all cases, start with the vector 1, 1, 1, and perform and iterate 3 times. Right, moreover, use at least 4 decimal digits without rounding, rather with rounding. We'll look at the solution to this. We'll look at the solution to this. Now, what do we do here? But before we look at the solution, I'm going to put one more question. I'm going to call it question C. Use the power method to estimate the remaining eigenvalue and the associated eigenvector. Right. We prepare the solutions to these problems as follows. Right, a couple of things remain extremely important here. So we are looking at part A. The focus is on the power method. We begin as follows by noting that here the dominant eigenvalue can be found by applying the power method to the matrix A. Thus, for AX lambda x, we continue. The dominant eigenvalue can be found by applying the the power method. So we're using the power method. Just okay, I'm not picking the right color. Just forgive me. All right. So now we continue. Right, so the dominant eigenvalue can be found by applying the power method to the matrix A. Thus, for AX equals lambda x, and lambda is the eigenvalue. Let us find these. So we understand that obviously we're going to start with the matrix A, and the matrix A has the entries minus 6, 0, 6, 4, 9, 2, minus 3, 0, 5, 1, 1, 1. Right, so if you multiply this row by this column, so that's going to be minus 6 plus 6, which is exactly 0. Multiply, so it's minus 6 by 1, which is minus 6, 0 by 1, 0, and 6 by 1, which is 6. So it's 6 minus 6, giving us the 0 entry. Row by column multiplication yields 4 by 1, which is 4, plus 9 by 1, which is 9, giving us a 13, plus 2, which is exactly 15. So this one gives us what? 15. The next thing is you do this row by this column multiplication so that you have minus 3, 0, 5, and this is exactly 2. So we have a 2 here. Right, with this said, what do we then do? What do we then do? We perform comparison because we have a 0 entry here. And obviously we are dealing with the dominant. We are dealing with the dominant eigenvalue. Now, it is sensible to say the number 15 being the most dominant, but also because we need to compare with the 1, 1, 1 vector, we attempt to achieve that. And now there's a 0 here, which we cannot be able to change, but we can be able to factor out 15, the largest one. Factoring out 15, the largest one is going to produce a 0, a 1, and then it's going to produce 2 out of 15. Like this. And simultaneously, it is evident that this is the same as 0, 1, then You have 2 divided by 15, which is 0.133. 3. Okay, how many decimal places, how many decimal digits? 4. Okay, use at least 4 decimal digits with rounding. So now we have 4 of them here. Yes, 4 of them. So this is exactly what we have. So this is the one. Next, because now we've got this, we take exactly this here, which is some eigenvector, and then we continue with the process. So we take the matrix A still with the entries minus 6, 0, 6, 4, 9, 2, minus 3, 0, 5. We multiply it by the vector x. In the AX, in the eigenvalue problem equation. So we take the 0, 1, 0.1333. So we have 0, 1, which is exactly now 0.1, like this. So what do we get out of these? Okay, so now you continue with the multiplication. So if you multiply minus 6 by 0, you get exactly a 0, 0 by 1, you get a 0, and 6 by this, which is 0.8, 1, 2, 3, like this. Then you do row by column multiplication, which means 4 by 0, 0, 9 by 1 is exactly 9 plus 2 by this. Okay, that gives us exactly 9.2667. Right, here doing row by column multiplication, this by that is 0, this by that is 0, 5 by this. 0 point 6, 6, 6, then 7. Okay. The next thing is now we look at these entries and we need to pick the dominant, the biggest one, the biggest entry out of this, but also to achieve the 1 as well. But we're dealing with the most dominant entry. And now it is clear that it is this one, 9.2667. Which is 0.0863, 1, 0.0719, like this. Next. So how many iterations were discussed here? Let's see. Consider this. Yeah, okay. And iterate 3 times. 3 times. So let's use the third one. Okay, let's see. Yes. Use at least your and iterate 3 times. 3 times. So let's do the third time. Right, during the third time, we take still the matrix A. And then 492 minus 305. We multiply by 0.08631, 0.0719. And this, if you multiply this, what do you achieve? So let's use our calculator. Right. Right, so using a calculator would have minus 6 by this. So it's minus 6 by 0 0.0863. 0 by this is 0 plus 6 times 0.0719. Okay, so what we're then getting here is exactly that entry. Okay, obviously to 4 decimals, it's the minus 0.0864. And then now you multiply this with that. Okay, so 4 times 4 times this 0.0863 plus 9 plus 2 times 0.0719. So and this gives us 9.489. And then the bottom row also. So you have also minus 3 times 0.0863. This by that is 0 plus 5 times 0.0719 equals. Right, so what we're getting is 0.1006. Okay. And then now with this said, we proceed. So what is the meaning of this? Right, the meaning of this here is that when we multiply, we're getting the minus 0.0864, 9.484, 0.1006. And then now you're going to pull out the biggest one. So that is 9.489. And then now here it's going to be 1. And then here now you want to divide these by that. Let's use some division. Right, so if you do the division, what you're then going to achieve is you take the 0.1006, you divide by 9.489, like this, which is what you're going to get then is that you have 0.4 decimals, 0.0106. Okay, so that is the bottom one, and then you have a 1. And then now the top one here also, if you divide this one by this, so minus 0.0864 minus 0.0864. You divide by 9.489 minus 0.0091. And the answer is minus 0.0091, 0.0106. Okay, that's fine. So this one here is minus 0.0091. Okay. And so here is the implication of these computations. After 3 iterations, we obtain this that sits here is the lambda. So you obtain lambda equals 9.489 x. And you obtain x, the vector, minus 0.0091, 1, 0.0106. Okay, so we have that. Right, but I'm going to make this inference here to say after 10 iterations, which is possible to do, we obtain. Okay, we have not gone up to 10 because the method is clear. But if we were to continue to 10, this is 0.123, 1, 0. Right. So we have this. We have this. And I want to make a note, write a note here. I want to write a note here. Moreover, right, it is possible to find the eigenvalues of the matrix A and the corresponding eigenvectors. Now, with this said, then thus for, let's just say that thus the eigenvalues are thus the eigenvalues are lambda equals -4, lambda equals 3, lambda equals 9. For lambda, for example, for lambda equals 9, the eigenvector is. So the eigenvector for lambda equals equals 3, the eigenvector for lambda equals -4. The eigenvector is okay. In which case you can call the eigenvector vector x. The eigenvector is -3 minus 14 over 13, 1. Okay, now we're done with part A. Use the POR method to estimate the eigenvalue of the least absolute value and the associated eigenvector. So now we're going to deal with the least one, but I said ready to use the POR method. You don't need to compute the You don't need to compute the eigenvalues first. That's the point. But now we're focusing on part B. But there's a remark here that the smallest absolute value can be obtained by computing the inverse of A. Now we're dealing with the smallest one because we dealt with the largest one in terms of the magnitude, but now we're dealing with the smallest one. And I want us to draw a comparison between the two approaches. And then also the one that is intermediate in terms of its magnitude. So the smallest absolute value can be obtained by computing the inverse of A and then using the power method. Because why does it work to compute the inverse and then using the power method? Well, because we reason together that AX equals lambda x is sort of the eigenvalue problem that we study. Solving for x means, therefore, we have x equals what? Right, x equals, right, so you can get x by saying x equals, so you multiply by the inverse of A lambda x. Like so. Like so. So it is possible that at this point you can actually then decide to divide by lambda so that you have x over lambda, and this is equal to, is then A inverse x equal to 1 over lambda x. And we look at the converse of this reasoning. And conversely, right, so as a converse, we actually can consider that if you have A inverse x, which equals mu x, goodness me, this means that we can get x. We can be able to get x from this. So if we are here, we just call this one mu. Calling the 1 over lambda mu so that we look at the whole thing in reverse, in a converse fashion, look at the mathematical converse. This would mean, therefore, we would write once again A inverse x equals to mu x. And what is all this? And now we can solve for x out of this, meaning x is the same as A inverse x, which is A mu x. So in other words, you can just multiply both sides by A to make x a subject. In each case, obviously, we're attempting to solve for x. And what is the meaning of these? This is then AX. is equal to, you can divide by the mu again, so that AX is 1 over mu X. Right, so in other words, this is true in both directions. Okay, so, but what is the significance of these? Well, the significance of these is given the matrix equation here, we can be in a position to find the, or to estimate this, the eigenvalue associated with the smallest eigenvalue in terms of its magnitude. It is worth mentioning that this proves that right, it proves that if you have the lambdas, the many eigenvalues, a finite number of them, are the eigenvalues of A, if and only if, oops, okay, if and only if, that's what I'm trying to write here. If and only if. Okay, this proves that lambda 1, lambda 2 up to lambda n are the eigenvalues of A if and only if the eigenvalues of A inverse are powerful results. 1 over lambda 1, 1 over lambda 2, and so on. So to get the eigenvalues of the inverse matrix, you just reciprocate and just to make those eigenvalues 1 over, and they will then be eigenvalues of the inverse matrix. Then what is then the implication of these? Hence, the eigenvalue of A with the smallest absolute value is the inverse of the eigenvalue of the matrix inverse with the largest value. So we are effectively then saying, so compute A inverse and apply the power method. Okay, we're saying this proves that lambda 1, lambda 2, up to lambda n are the eigenvalues of A if and only if the eigenvalues of A inverse are 1 over lambda 1, 1 over lambda 2, 1 over lambda n. Hence, the eigenvalue of A with the smallest eigenvalue is the um, is the inverse of the eigenvalue of, yes, right. Hence, the eigenvalue of A with the smallest eigenvalue is the inverse of the eigenvalue of A inverse with the largest eigenvalue, with the largest value, magnitude. Okay, so we can just study the inverse and the matrix A interchangeably in that with that understanding. But so what do we need to do here? To deal with the smallest magnitude and the largest magnitude eigenvalues, what do we do? So compute the inverse of A and apply the power method. Why? How would computing the inverse of A and applying the power method work? It's just going to work because the eigenvalue of A with the smallest eigenvalue, absolute value, which is what we want, is the inverse of the eigenvalue of A inverse with the largest. So what are we looking for here? The eigenvalue with the least eigenvalue, absolute value. But with the least eigenvalue here, normally we deal with the dominant. So we're going to find the inverse of the matrix A. By good luck, it's already there. And with that inverse, then the inverse is going to produce the absolute value, or rather the eigenvalue with the largest magnitude. All right, and that is the one we want. All right, so we continue. We continue. Let's continue. Right, so now we are still focusing on the part B. Okay, so how do we do the part B? So we're going to deal with the inverse of A. What is the inverse of A? Which is minus 5 out of 12. 0, 1/2. 13 out of 54. 1 out of 9. Minus 1/3. Minus 1/4. 0 and 1/2. So what do we do here? We continue like before. And now we are dealing with the second part, the smallest absolute value. Okay, dealing with the smallest absolute value, we take the matrix minus 5 out of 12, 13 out of 54, minus 1/4, 0, 1 out of 9, 0, 1/2 minus 1 out of 3. 1/2. One, one, one. Right, so if you multiply these, we're looking for the smallest absolute value here. So, but the smallest absolute value is going to be, the smallest absolute value of A is going to be the biggest absolute value in the inverse we are looking at, because the power method deals with dominance, the largest things. So now we're going to look for the largest things in the inverse, and they're the smallest things in the matrix A. All right, so if we multiply these by this, these by that, these by that, and we find the sum. These by that, these by that, these by that, we have 0, 0, 1. This by that, this by that, this by that, we have 0 point. Now look for the biggest one. Which one is the biggest one? The biggest number here. The biggest number is 0.25. The biggest decimal, so we factor it out. And then now it means we're going to divide this one by the 0.25 double zero, and that is 0. Quadruple 3. If you divide these by 0.25, you get 0.0741. You divide this by that, you have a 1. Okay, remember the power method is just about the largest magnitude. So now we are looking for the largest magnitude absolute value, which is the dominant, or which is the largest in the inverse matrix. Okay. Next, let's do a couple of iterations here. So still we consider the inverse matrix, and we have minus 5 out of 12, 13 out of 54, minus 1/4, 0, 1/9, 0, 1/2, minus 1/3, 1/2. So now it is then, now you have these ones. You take this vector, which is sort of the eigenvector, associated with this eigenvalue. You plug it in this position. So it's 0.3333, 0.0741, and then 1. Right, we multiply, do row by column multiplication. This minus 5 out of 12 by this, 0 by this, half by this. You add everything. So what this produces is that we have 0.3611 minus 0.2449, 0.4167. Pull out the largest one, which is 0.4. Right, so if you put out the largest one, which is 1, 0.5877, six, six, 7. After 2 iterations, right, after 2 iterations, we estimate the dominant eigenvalue of A inverse as 0.4167. 0.4167. And the corresponding eigenvector as this is the corresponding eigenvector, which is the 0.A667 minus 0.5877, then 1. What is the meaning of all this here? The eigenvalue of least magnitude of A is therefore lambda, which equals 1 over this. Okay, because this one is the biggest one. Is the biggest one for the inverse relative to 0.3, 0.2, 0.4. It is the biggest one. So now the eigenvalue of least magnitude is therefore now we want to get that of A, the eigenvalue of the least magnitude of A. So we divide, we take the reciprocal, and it is 4167. And this is 2 point like this. And the corresponding eigenvector is the one given above. That is 0 point. Okay, let's just say it's most certainly the one given above. It's enough because we've already stated that. But my point is, we have been able to answer this question. What is the question? The dominant eigenvalue of A, we found it. We used the power method to estimate the dominant eigenvalue. And then also we used the power method to estimate the eigenvalue of the least absolute value. So now, in both cases, we estimated the eigenvalue of the least magnitude and the eigenvalue of the least absolute value. Right, so either way, we are then done with this. The one of the least absolute value. So for the least absolute value, we find the inverse. And we deal with the inverse, looking for the dominant one in the inverse, and then we take 1 over. But for the dominant eigenvalue, we just use the matrix A. Okay, what about the part C? We need to use the power method to estimate the remaining eigenvalue because there's a part where we said it all the three eigenvalues is a 3 by 3 matrix this, so it has 3 eigenvalues. But use the power method to estimate the remaining eigenvalue and associated eigenvector. Right. So need to estimate the remaining one. Let's look at how we do that part. But also, I mean, we took a chance to state, okay, so the eigenvalues themselves are -439, so there are 3 of them. The dominant one in terms of magnitude is the 9, and we have been able to see through the estimation that we got closer and closer to the 9 in our pursued for this computation. It was an 8.99 after 10 iterations, meaning we're very close to the 9 up there. And so it's a very interesting observation that indeed the dominant one of the largest magnitude is 9, and we're close to it using the power method. So indeed the power method sort of converges to the most dominant, but also if we're looking for the least magnitude absolute value, rather eigenvalue, we I showed the power method also converges accordingly. Okay, we have seen also in this part B. Okay, for instance, in the part B, we saw that the eigenvalue is 2.4 of the least magnitude. If you look at it's 2.4, so it was closer to 3 of the least magnitude because 3 magnitudes here, 3, 3, 4, and 9. 3 is the smallest one. So the 2 point something was getting closer to 3. So if you could do like up to 10 iterations, you could get very close to 3. So indeed, the power method works wonderfully. So it converges to the correct one. So using the power method, we do not have to find the eigenvalues. We can just use the power method all the time to estimate instead of. So now in linear algebra we find the eigenvalues. So how else can we deal with these? So we can decide to say, okay, instead of having to do the absolute value, finding the absolute values, we can just use the power method to estimate. But we need a starting eigenvector. We need a starting eigenvector. Okay, let's just proceed and do the next part. What is the next part? The next part focuses on a couple of things, but focuses on the intermediate one. Okay, for the dominant one, for the dominant of the eigenvalue of the largest magnitude, we use the matrix A. Of the least magnitude, we use the inverse. And then now I want us to have a discussion about the intermediate magnitude, eigenvalue of the intermediate magnitude in terms of what we do there, because these are the things that come in the exam. Okay, that is a part C. Part C. Okay, let's look at part C here. Okay, let's look at part C. To do part C, it's all interesting stuff. Let's just get cracking with it. Okay, there's a discussion about the intermediate one, and I want us to go through the discussion that is quite very, very helpful. All right. Okay, we continue. We continue. Right, we continue, please. Just one sec. Let's go through the discussion about the intermediate one. The couple of things that remain very important. The two calculated. The two calculated eigenvalues right, lambda equals approximately 9.2667 and lambda 2 approximately 2.4 triple zero. So we continue. We continue. Right, we note that both lie in the union of the disks. Right, so the couple of disks here, like your D2 and D3. The two calculated eigenvalues, which is lambda approximately 9.2 that and the 2.4, both lie in the union of the disks D2 and D3. I'm going to comment on the disks, the Gerschgorin disks. Right, so hence, we know Okay, we continue. Hence, we know from 1. Okay, my system is refreshing a little bit. So I'm just a little bit slowing down because I'm sure that it is the system that is making my writing to appear after a little while. That the remaining eigenvalue right, the remaining eigenvalue lambda 3 must lie in D1. Okay, I'm going to comment on the Gerschgorin disks. Right in D1. Okay, must lie in D1. Right now, the couple of things I want us to consider, and that would be that lambda 3 itself must be near -6. Must be near -6. All right, so we continue. Right, so must be near -6. Okay, when I discuss the Gerschgorin circles, however, in order to use the inverse power method, we must shift the eigenvalues Okay, there's going to be a shift of the eigenvalues. So if lambda, for example, is an eigenvalue of A with corresponding eigenvector X, then for example, which is lambda X. Which is lambda plus 6x. Okay, so if lambda is an eigenvalue of A with corresponding eigenvector, then obviously we're dealing with the intermediate case, please, because we dealt with the least magnitude and the largest magnitude. And now we're dealing with the intermediate case, and we're looking at the eigenvalue problem where lambda itself is lambda x. And now you have that we actually therefore are able to transform this system in this particular manner. And this transformation of sort of the subtraction of the minus 6x here, we put the identity matrix because we are having a matrix A on the left of the equation. Okay, the observation then is that, so I want us to note something here. So obvious at this point here, you have the lambda plus 6x, and then we proceed. Hence, the eigenvalues of A plus 6IR, lambda 1 plus 6, lambda 2 plus 6, lambda 3 plus 6. Okay, we are continuing and we're analyzing these. Okay, I'm going to speak about the Gerschgorin circles, please, and to justify the use of the number 6 here. That the eigenvalue is close to -6, but we know that the eigenvalue is -4. We saw that because we had the 3, we had the 9, and we got -4. I wrote it earlier. So obviously, but we're speaking of estimates here, and using the Gerschgorin circles, we estimated to be close to -6. Okay, I'm going to look at the graphical representation of the Gerschgorin circles here. But now I want to mention also that these hence eigenvalues of the matrix A plus 6i are this, okay? And the eigenvalues, right, and the eigenvalues of A plus 6i are 1 out of lambda 1 plus 6, 1 out of lambda 2 plus 6, 1 out of lambda 3 plus 6, and so on. Okay, for the inverse, we just, through the argument raised, we just take the reciprocals of those matrices, of the eigenvalues. Okay, what is the meaning of this? We note that. Right, we note that the eigenvectors, right, the eigenvectors remain unchanged. This is very important. Okay, so the eigenvalues keep changing, but the eigenvectors remain what? They remain unchanged. But also since lambda 3 is near -6, lambda 3 plus 6 will be small. Thus, the 1 out of lambda 3 plus 6 will be the dominant eigenvalue of the matrix A plus 6i compared to lambda 1 plus 6. Double five. And okay, and also the 1 out of lambda 2 plus 6 is about 1190. Okay, well, I want us to discuss this, obviously. But now I want to first mention that, and so the power method can be used to find it. But first, we use the most popular Gauss-Jordan method to obtain A plus 6i. All right, a couple of things. Hence, the eigenvalues of A plus 6i are these. And the eigenvalues of the inverse of that are these. Note that the eigenvectors remain unchanged, but since lambda 3 is near minus 6, lambda 3 plus 6 will be small. Okay, very small. If lambda 3 plus 6 is small, then the reciprocal or the multiplicative inverse will be the dominant eigenvalue of the inverse matrix compared to lambda 1 plus 6, which is approximately that, and lambda 2 plus 6, which is approximately 0 point that. And so the power method can be used to find it. Okay, I want to, okay, I'm going to elaborate on the use of the Gerschgorin disks and the justification of the fact that the minus 6, the eigenvalue is closer to minus 6 using the Gerschgorin circles. But first things first, I want us to demonstrate the power of the power method, or the actual strength of this power method for the intermediate eigenvalue, or the eigenvalue of. So we start with this matrix here as follows. Right, we start with this matrix here as follows. So obviously, I want us to remember something first for this to make sense. Let's remember the matrix A that we started with. We remember that the matrix A is this one. Right, so now if you have the A plus 6i, okay, now we're gonna just like add 6 to each of the diagonal entries. If you add 6 to each of the diagonal entries, so if you add 6 here, 6 minus 6 is 0, 0, 6. Okay, because the identity matrix only has ones in the main diagonal. So if you add a 6 here, it's going to become a 15, but the 4 is going to remain the same. And then you're going to have a 15, and then a 2, and then minus 3, 0. And then after you add a 6 to the 5, it's going to be an 11. So that is that. But now using the goals you're done, so you have this, then you have 4, 15, then 2, you have minus 3, 0, 11. And then you have 1, 0, 0, we have 0, 1, 0, 0, 0, 1. So what do we get here? We need a 1 here because we want to get the inverse of this matrix. So we interchange rows 1 and 3, putting row 3 in the first position. So that's 0, 11, double 0, 1. The second row is unaltered. And then you have 6, so which is minus 3, 0, 11, double 0, 1. Okay, let's look at 4, 15, 2. And then 0, 1, 0. Which is double 0, 6. 1, 0, 0. Right, and then now we're gonna want to get the inverse, or like as usual in linear algebra, we multiply the first row by minus 1/3. 11 out of 3 here, 0, 0 minus 1/3. 4, 15, 2, 0, 1, 0, 0, 0, 6, 1, 0, 0. And then you have 1, 0 minus 11 out of 3, 0, 0. And then you have 4, 15, 2. And then you have 0, 1, 0. 0, 0, 6. 1, 0, 0. Row 2 minus 4, row 1. 1, 0 minus 1 over 3. 0. 15. And if you do here, multiply by minus 4 and you add to this, that's like a 44 out of 3 plus 2, which is a 50 out of 3. And then, okay, so this one, 0. This one, 1. This one, 4 out of 3. 0, 0, 6. 1, 0, 0. Okay, now what is this? It's exactly this. But now we want to get a 1 here. So which means that we're going to keep the first row the same. 1, 0 minus 11. 1, 0 minus 11 out of 3. 1, 0 minus 1/3. Okay, then you have 1 over 15. Which is 0, 1. And then you divide this one by 15. Okay, because you multiply, if you divide this one by 15, then it's like you're going to have 15 by 3 in the denominator, making it a 45. So it's like a 50 out of 45. 5 goes how many times into 50? It goes 10 times into 45, 9 times. It's 10 out of 9. Right, so 0, which is 1 out of 15. 15 here. Okay, then here we multiply by 1/6. Which is 1/6 double 0. And then the next thing is to get so the previous matrix is row equivalent to this. Row 2 minus 10 over 9, row 3. Okay, I want to get a 0 here. But obviously, if you multiply this one by minus 10 over 9, what does this become? So 10 out of 6 would give us what? Would give us 5 out of 3. And it is minus 5 out of 27. So if you multiply this one by by minus 10 out of 9, one 0 minus 11 out of 3. 1, 0 minus 1 out of 3. I can just change this one. Let's row reduce it. row 1 plus 11 out of 3, row 3. Okay, now plus 11 out of 3, this one multiplied by 11 out of 3, it becomes 11 out of 18. Multiplying this by 11 out of 3, it becomes 11 out of 18, and then plus 1. So 11 out of 18 plus 1 is like 11 out of 18, then this one is 18 out of 18. So what is 11 plus 18? Right, so we have 11 plus 18 giving us a 29. A 29 out of 18. And then we have this one here, which is row 1 plus 11 out of 3, which is 0 minus 1 out of 3. Okay, I need to cross-check the matrix inverse, please. And make sure that this matrix inverse is the correct one, because we're just doing it. So there is a chance of human error. Okay, we want to find the inverse of this matrix, A plus 6i. I want to also use computer algebra to test this. I want to use computer algebra to test this. Which is 0, 0, 6, 4, 15, 2, minus 3, 0, 11. Okay. Right, a couple of typos. This is fine, you see. Okay, we might change this one. So if you say now 11, just I want to do a check quickly. Okay, because you multiply row 3, this one, by 11 out of 3, and then you add to 1. Let me just check this. Can come here. Just make sure you get the correct answer. Right, so now I'm effectively saying here, so we're having the 1 out of 6. And we multiplied by 11 out of 3. So 1 out of 6 by 11 out of 3, you add to 1. Which is exactly 29 out of 18. So there is let me see, a small error. Okay, yeah, there's a small error here because this is 0. This is 0. But now it was accidentally written as a 1 here. See, it's 0, 0, 1, 3. Okay. Check this. So this is 0. Let's write this one as 0. Okay, so this one is 0. And then this one is therefore going to become, if you multiply, it's going to be, yeah, this by this, 11 by 6, 1 over 6 is going to be 11 out of 18, which is exactly what I expected. Right, so the inverse is now correct. I used also computer algebra to check it. So the conclusion then is that hence a plus 6i 11 out of 18, 0 minus 1 out of 3, which is minus 5 out of 27. One out of 15, 4 out of 45, 1 out of 6, 0, 0. So this is what we get. Okay, when you get to this point now, the power method is applied. Right, obviously at this point using the power method, because we're dealing with the most intermediate, so we're going to take the inverse, which is this one here, zero minus 1 over 3, which is minus 5 out of 27, 4 out of 45, 1 out of 6, 0, 0. If you multiply this row by column, row by column, row by column, you get 0.277 like that. 7 minus 0.0296, 0.1667, 0.2777. Factoring it out because it's the biggest one here. Is the biggest one, so you factor the biggest one amongst the entries. You divide each of these by 0.2777, and that gives minus 0.1067, 0.6000. And then now you get 11 out of 18, 0 minus 1/3, minus 5 out of 27, 1 out of these, 4 out of 45, 1600, 1 minus 0.1067, 0.06. If you multiply these, what do you get? 0.4111 minus 0.1390, 0.1667. Okay, the biggest magnitude is 0.4111. We factored it out, and we have 1, 0.3380, 0.4, 0.54, and we make a couple of observations that after two iterations, one over lambda 3 plus 6 is a 0.4 triple one, which is coming from here. 0.4 triple one is coming from there. Lambda 3. 1 divided by 0.4 minus 6. Okay, we take the reciprocal of this and then we solve. We solve for lambda 3 from this, making it the subject of the equation, and that gives us minus 3.5676. X becomes the eigenvector, which is exactly 1 minus 3 minus 0.3380, and then 0.4054, which becomes the eigenvector 1, 0.3380, 0.4054. Okay, we give a comment here that after 10 iterations, which is 1 divided by 0.5123 minus 6, 4.123. Zero 0.359, 0. Right, after 10 iterations, we get this, like we did the 2 iterations. So, and we proceed to compare. To compare this with the result. when lambda equals -4. Okay, there's going to be an m that is going to come from the eigenvector factorization. I did not quite spend time on the on these because they're not very popular. But associated with this, when there's an m and an n, those numbers that are factored out of the eigenvector, I'm just gonna mention these in passing. All right, so um, okay. All right. Okay. Okay, I want to comment on the fact that you compare these result when lambda equals -4 and m, because the m is actually the 1/3, because the eigenvector is first obtained as 3m. 3m minus 14 out of 13m. So this sort of becomes the eigenvector. And one can choose this. You can factor out this and have this. Right, so that when m is 1/3, then you get the, you can choose m to be 1/3 because it's arbitrary, etc. Okay. But what is the significance of this? Right, so this one, put it in a block. And then you have x. Okay, if you take m to be 1/3 in this, that's going to be 1. Put the 1/3 is going to be minus out of 39, and then it's going to be 1/3. Okay. So, okay, just observe that. Right, you observe that. Which is 1 minus 0.3590 0.3333, like this. Compare this with the result when x bar is this. Let's check. Obviously, you can see that after 10 iterations, we got 1 and then this. Something I want to comment in the negative. I think that just be here now. X1 is 3x3. So x2 is, okay, I'm with you now. I'm just checking the signs here. I think there's a sign error. Because now you're going to have x2 is minus, yeah. And then the 2x1 becomes 3x3, and then it becomes 12, 14, which is minus. Okay. Right. I want us to observe this, but observe the sign difference in the middle entry. Right, so that you have, but you can see that the 1 and the 0.33 match precisely. They match most actually precisely, but you can see that there's just a sign issue here in terms of the fact that this is positive here, but obviously this side it is negative. The negative is indeed a very correct observation, but here this must be negative, this, because it is negative here. So this must be negative. Okay, because I'm just saying after 10 iterations, because it was sort of done in the textbooks, or I'm sure that somebody missed a sign here, etc. But it must be negative because you can see that our 2 iterations is negative. Just seeing the sign difference from the material I'm using, but yeah, it's negative, negative. So yeah, it actually works well. Now, observe this as actually very important that this M comes from the actual calculation process of the eigenvector. In other words, for lambda equal to -4, this is sort of this is the eigenvector, 3, etc. You can just choose the M, it's a common factor. But using the power method, we can see after 10 iterations, we get closer and closer to actually the eigenvector itself, because it's 1, then 0.3333, so we get close there, much closer. Okay, I want to give a comment about something extremely important here. I want to give a comment about something extremely important. As follows. I want to talk about, before we conclude our discussion today, if time allows, just a comment on the Gerschgorin. Gerschgorin's theorem. All right, so now let's look at the Gerschgorin circle, Gerschgorin circle theorems. Let me write a little bit big here. Oops. Right, let me write a little bit big because I want us to just have a brief discussion about this because it's very important for the intermediate eigenvalue, because the smallest and the largest we have seen we can deal with the matrix A and the and the inverse, but the Gerschgorins, right? We're continuing quickly. Gerschgorins circle theorems can be formulated as follows. So we have the matrix A, four, 9, 2, twelve, 0, 1 out of 2, 13 out of 54, 1 out of 9, minus 1/3, minus 1/4, 0, and 1/2. Okay, these are the matrices where the matrix started with. And with these matrices, theorem 1. Let A be an n by n matrix with the A ij's real or complex valued then all the eigenvalues of A lie in the union of the following n disks di in the complex plane. Di z minus ai is less or equal to the summation like so. I equals 1, 2, and so on. Di is simply the disk with center AII and radius equal to the sum of the absolute values of the entries in row I, which are not on the main diagonal. There's a theorem. Theorem 2. If K of these disks do not touch the other n minus k disks, then exactly k eigenvalues counting multiplicities lie in the union of those k disks. For the matrix A, above we have disk 1 Z in C, Z minus this plus 6, which equals 6. Disk 2 Z minus 9, which is 4 plus 2. Okay, we're gonna just look at where these numbers are coming from. Disk 3, Z is the element of the complex numbers such that Z minus okay, these Gerschgorin circles are very important when we are looking at the intermediate absolute value. So minus 5 here, and this is minus 3 plus 0. 3. Okay. These circles themselves, the Gerschgorin circles, are, if you are looking at the imaginary axis, so you can have a circle here, centered at 5, in another circle centered at 9 of radius 6 or less, something like that. Okay. Okay, well, we're running a discussion about the Gerschgorin circles, please. So there's a point I'm trying to drive towards here. And this one is a real part of Z. Disk 2, disk 3. Okay. Now with this actually mentioned here, what then can we observe at this point from this? Right. I want us to look at the according to Gerschgorin, 1 and 2, one eigenvalue lies in disk 1 and the other 2 lie in D2 union D3. According to Gerschgorin theorem 1 and theorem 2, one eigenvalue sort of lies in disk 1 and the other 2 lie in the union of the disks. Eigenvalue. Okay. Now, theorem 1 actually mentions that if you let A to be an n by n matrix with the aij's real or complex valued, so these are the entries in the matrix, then all the eigenvalues of A lie in the union of the following n disks, di in the complex plane. So you have the union of the disks such that here you have z in C, and here you have z minus the aii. So such that this is less or equal to the sum of the other entries that are of diagonal entries, So obviously, we understand therefore that the z minus aii of the matrix A. So in view of this, it means therefore the Gerschgorin circles would actually therefore have this z minus 6, z minus into minus 6, and then z minus 9, and then z minus 5. Z minus into minus 6, because these are the entries in the main diagonal, then here you're going to add the off diagonal entries. Right, so you find the summation of the modulus of the off diagonal entries where the I runs from 1 to n, because we're dealing with the n by n matrix there, like so. Now, moreover, in view of that, here you have 0 plus 6. Okay, so obviously at this point, you're going to actually proceed to add the off diagonal entries outside outside um if you look at, for instance, at the entry 9, what is outside the entry 9? Right, outside the entry 9 you'd have 4 and 2. Right, outside the entry 5 on the main diagonal would be minus 3 and 0. Right, so the off diagonal entries then of the right off 6 would be what? There would have to be a 9 here. Just checking on these, because the off diagonal entries here you'd have actually exactly a 0 and a 9. Right, that's what you'd need according to the theorem 1. Theorem 2, if k of these disks do not touch the other n minus k disks, then exactly k eigenvalues counting multiplicities lie in the union of the k disks. Right, so we know that this is very important, because it might happen that if k of these disks do not touch the other n minus k, because not all the disks touch. Right, so obviously at this point, you really can see that two sort of the disks touch, but the others don't. The others don't. All right. So as said already, there is a modification here that is necessary. To then say the one that is centered at 6 would have to, the off diagonal entries of 6 would have to be, provided I made a typo here. See the matrix A. Oh, you see? That entry is what? Ah, this entry is 6. That's the reason why I'm wondering why. Okay, so there's an entry that is 6, but that entry was written correctly here. I was wondering why. So this entry is 6, apologies there, so that this is correct. Now, with this said, obviously this will be the Gerschgorin circles. According to the Gerschgorin 1 and 2, the eigenvalue lies in D1. One eigenvalue lies in D1, and the other two lie in the intersecting ones. Okay, so that is what the theorems vehemently both agree, because if k of these disks do not touch the other, n minus k disks, so you have disks that do not touch, like 1 does not touch 2, then exactly k eigenvalues, counting multiplicities, lie in the union of those k disks. So one disk, one eigenvalue is going to lie in 1, and then the other 2 is going to lie in the union. What is the meaning of this? Okay, we're concluding, please. What is the meaning of these? Well, it means that the minus 6 is going to lie in disk. Okay. Okay, let's just explain, elaborate. Okay, we are finishing, please, but it's the point I'm trying to get to, but I'm going to be really very fast. Right, for the 3 by 3 matrix, minus 606. Nine, 2. Minus 305. Minus lambda. 06 minus lambda. Oof. Okay, main diagonal entry is not obviously. So the minus lambda, but yeah, I'm trying to just elaborate on, I know that you know this very well, but we use these to find the eigenvalues. So the eigenvalues will lie in the disks, in the Gerschgorin disks. So I want us to drive towards that point. And therefore, A minus lambda I equals 0. I'm not going to waste a lot of time there. So here it means that lambda becomes, so this becomes 9 minus lambda. which is lambda minus 3. And then this is minus 4, 3, 9. We give the comment that this confirms our earlier conclusion. Because minus 4 lies in disk 1, while okay, we're concluding, please. While lambda equals 3 and lambda equals 9, the other eigenvalues lie in D2 union D3. Okay. So this confirms our earlier conclusion because you have that observation there, that those eigenvalues lie in the respective disks, because those disks do not all touch. There is a disk, the one that is centered at minus 6, does not touch the others. Because it doesn't touch the other two, this one does not touch the other two, according to this theorem here, if the k of this disk do not touch the other n minus k disks, then exactly k, the ones that do not touch, then exactly k eigenvalues counting multiplicities lie in the union of those disks. Okay, so in other words, you have those eigenvalues that lie in the union, and obviously you can see that in these disks here, you have those two eigenvalues. What are the eigenvalues? The one for lambda equals 3 and 9, because you can see that 3 and 9, 9 is here and 3 is there, and they are in the disks, but minus 4 is a number that is there, so that we have that the minus 4 would lie in disk 1. But I mean, what is the point of this? What is the essence of this? The essence of this is the discussion we had here about the intermediate eigenvalue. Because now we are saying in the part C, the two calculated eigenvalues, we're finishing please now, lambda equals this and lambda, we estimated those, both lie in the union of the disks. Yes, these ones both lie in the union of the disks we've spoken about. Hence, we know from Roman figure 1 is a discussion that I've just included now, that the remaining eigenvalue must lie in D1, must lie in D1. That is, lambda 3 must be near minus 6. So the one that, so in other words, for the intermediate eigenvalue, we consider these Gerschgorin circles in this and the Gerschgorin circle theorems. And then now we realize that, okay, from the Gerschgorin circles, we use the -6. We use that -6. Where is the -6 coming from? It's the center. What is the -6? The -6 is actually the center of one of the disks. And being the center of one of the disks, we used it wonderfully here. And we subtracted it here and used it here. And we're able to give an estimate of the lambda 3. Lambda 3 being the eigenvalue that lies close to okay, this is also minus this, because this is like 2. One over this is like, so this is going to be like -2, yeah, -4. Sorry. It demonstrates just the fact that we can use these Gerschgorin circles in the power method to solve these problems. Okay, this I believe made a bit of sense. In particular, the dominant case, the least magnitude case, and the intermediate case uses the Gerschgorin circles. I must thank you for joining us today. I know that we've dragged much. See you. I need to check my the thing. Okay, the approximate time is 4. The approximate time is 4, and then I can communicate. Right. So yeah, the approximate time is 4, but I'm gonna check the load shedding thing schedule, because yeah, it shows the one. We must be fine tomorrow. If I set the time at 4, yeah, we're okay. According to the load shedding schedule, there's no problem at 4. So you can meet at 4, and then I'm planning lots of stuff that we'll discuss, exam-oriented stuff. So yeah. Thank you so much for joining us. See you tomorrow at 4 p.m. Thank you.